Have you ever pondered the amount of energy needed to travel through time? Well, sit tight because we're about to embark on a journey into the realm of time travel, a concept that is often more at home in science fiction than in our everyday reality. Throughout the ages, the idea of time travel has ignited the human imagination. From H.G. Wells' The Time Machine to the Back to the Future trilogy, and even in the more recent Avengers Endgame, we've seen characters hop between different eras, altering the course of history or reshaping the future. But these are, of course, fictional narratives. Real-world time travel, if it were possible, would be a whole different kettle of fish. Time travel is not just a matter of having a fancy machine or a magic spell. It is deeply rooted in the laws of physics and comes with its own set of paradoxes. The most famous among these is probably the grandfather paradox. Imagine if you traveled back in time and accidentally caused your grandfather's early demise. This would mean you were never born, which in turn means you couldn't have traveled back in time in the first place. A true paradox. But let's not get too lost in the realm of paradoxes. Instead, let's focus on a crucial aspect of time travel: the energy required. Think about it. If traveling through space requires tremendous amounts of energy, and it does, then traveling through time, which is another dimension entirely, would likely require even more. We're talking about unimaginable amounts of energy, the kind of power that could light up entire galaxies. But what does science have to say about time travel and the energy it would require? Let's delve into it. Science has a lot to say about time travel and the energy it would require. The concept of time travel has always been a fascinating topic, not just for science fiction enthusiasts, but also for scientists. Albert Einstein's theory of relativity, for instance, provides a scientific framework that allows for the possibility of time travel. Einstein's theory of relativity is a cornerstone of modern physics. It tells us that space and time are intertwined into a four-dimensional fabric known as spacetime. What's more intriguing is the theory's implication that the fabric of spacetime can be warped by mass and energy, leading to phenomena like gravitational waves and black holes. Now let's talk about wormholes. In the context of time travel, a wormhole is a theoretical bridge through spacetime that could create shortcuts for long journeys across the universe. Wormholes are solutions to the Einstein field equations for gravity that are theoretically possible given the right conditions. The catch, however, is that they would be extremely unstable and would require enormous amounts of energy to keep open. So, how much energy are we talking about? Well, according to some calculations, to keep a wormhole stable enough for a human to pass through, you'd need the energy equivalent to the mass of a star. That's right, a star. This is far beyond our current technological capabilities and underscores just how challenging the prospect of time travel is. Furthermore, the energy required to travel through time would likely have profound and unpredictable effects on the very fabric of space-time itself. These effects could range from the creation of alternate timelines to the potential for catastrophic disruptions of the space-time continuum. So, it appears that time travel, as we understand it, would require an almost unfathomable amount of energy. But are there any real-world examples that might support this? Well, stay tuned for our next segment, where we delve into the real-world evidence of time travel and the energy it requires. In fact, there are some real-world phenomena that could potentially support the concept of time travel. One of these intriguing examples is the phenomenon known as time dilation. Time dilation is not just a concept out of a science fiction novel. It is an actual observable phenomenon that is central to Albert Einstein's theory of relativity. In simplest terms, time dilation suggests that time moves slower for an object in motion compared to an object at rest. To put it in perspective, imagine a clock on a fast-moving train. According to time dilation, this clock would tick slower than a clock that's standing still at the train station. A perfect real-world example of time dilation in action is the Global Positioning System, better known as GPS. The satellites used for GPS are in constant motion around the Earth, and because of this, their onboard clocks experience time dilation. The clocks on these satellites tick slower than the clocks on Earth by about 38 microseconds per day. It might not seem like much, but without correcting for this time dilation effect, the GPS system would be off by about 6 miles per day. Time dilation is also observed in particle accelerators. These machines accelerate particles to almost the speed of light. At these speeds, the particles experience significant time dilation. For instance, unstable particles that would normally decay in a fraction of a second can last much longer when they're moving at high speeds in a particle accelerator. This is because, from our perspective, their internal clocks are ticking much slower than usual. These examples suggest that time travel might be possible, but it still seems to be beyond our current technological capabilities. But what if we could harness the necessary energy? Time travel, which once seemed like a far-off dream, could become a reality. And we have real-world evidence that hints at its possibility. So, buckle up. The journey through time might just be around the corner. Harnessing the energy required for time travel is a monumental task. This statement may sound daunting, but it's not far from the truth. Let's take a look at why. Our current state of energy production and storage is impressive, to say the least. We've harnessed the power of the atom, tapped into the sun's energy, and even learned to store power in tiny batteries that can fit in the palm of our hands. But even with these great strides, we're still far away from generating and storing the immense amount of energy that would be needed for time travel. Why is so much energy needed, you may ask? Well, consider this. Time travel isn't just about moving through time, it's about moving through space as well. If you were to travel back in time, you wouldn't want to end up floating in the void of space because the Earth was in a different location in its orbit around the Sun. To avoid that, you'd need to precisely calculate and execute a move through both space and time. The energy to do this would be enormous. Some theories suggest that to open a wormhole large enough and stable enough for a human to pass through, we'd need the energy equivalent to that of a star. That's a staggering amount of power, far beyond what we can currently produce or store. And then there's the challenge of storage. Even if we could generate that much energy, where would we put it? Our current batteries and power grids wouldn't be able to handle it. We'd need a new, revolutionary way to store and transport this energy safely. These challenges may seem insurmountable, but remember, there was a time when flying was considered impossible, and look at us now. We're constantly pushing the boundaries of what we're capable of. So, while we might not be able to harness the energy needed for time travel right now, who knows what the future might hold? The future of time travel remains a fascinating and elusive concept, yet it's not entirely beyond the realm of possibility. As we look ahead, we see a world where advancements in energy production and storage could potentially make time travel a reality. Imagine for a moment an energy system so advanced, so efficient, that it can bend the very fabric of space-time. This would be a system harnessing the power of the cosmos, the energy of stars, or even the potential of black holes. It's a lofty ambition, but one that, theoretically, could be within our reach. Yet, even if we were to master such a feat, we must ask ourselves some difficult questions. What are the ethical implications of time travel? If we could journey into the past or future at will, how would that reshape our understanding of responsibility, of cause and effect? Consider too the practicalities. How would we govern time travel? What rules would we put in place to avoid the potential chaos of altering timelines, of changing history? These are questions we must grapple with as we strive to unlock the secrets of time. And then there's the question of accessibility. Should time travel become a reality, who gets to use it? Do we reserve it for scientists, for explorers, or do we democratize it, allowing anyone and everyone to journey through time? These are just some of the challenges we would face in a world where time travel is possible. And while they may seem daunting, they also serve as a reminder of why we explore, why we question, why we innovate. Because each challenge represents a puzzle to be solved, a mystery to be unraveled. While the dream of time travel remains largely in the realm of science fiction, the science behind it continues to evolve, and who knows what the future might hold. We may not have all the answers yet, but we're certainly asking the right questions. And in the pursuit of knowledge, that's often the most important step.